So we've discussed the importance of polarization. What about the importance of depolarization? And in particular, what about Hyper-Rayleigh scattering measurements, where we are integrating over the contributions of many individual sources. Sorry, that was my dog there. Over any individual sources that incoherently sum to produce some macroscopic signal. And how do we treat that? How do we consider that in terms of the molecular properties, in terms of the macromolecular properties, in terms of the observables? That's the objective. We're going to do it in two parts. We're first going to consider just what is a working definition of Hyper-Rayleigh scattering, and how do we discriminate between that and second harmonic generation operationally? And then can we work through a simple example for something that is rod-like, where things are relatively easy to understand in this model system. So let's consider this model system in which we have a plane wave coming in, and we're detecting the doubled frequency coming out. And I'm showing the source as just being a sphere for the sake of simplicity. And we're asking, if we're measuring in this particular scattering angle, are we measuring something that is coherent or incoherent? And the argument is that if you have a bunch of particles, a bunch of sources, SH-reactive sources on the surface of this sphere, well, then in that case, those individual molecules are collectively interfering to give you a coherent signal coming off in this direction with a well-defined direction, well-defined polarization state. However, in a single laser pulse, we also have interference of that signal with the signal produced from the adjacent sphere. Now, what will happen if we have many of these such sources is that the net result will be some sort of speckle pattern. And that speckle pattern will be a coherent signature of the spatial relationships of all of the SH-reactive sources, both on the surface of the sphere and the individual at the molecular level. So obviously, if for a single pulse femtosecond laser experiment where the dynamics are frozen, what we get is a coherent signal resulting from the net interference of everything interacting at the sample. However, we generally don't stop at just one single pulse. So if we're going to be integrating the measurements of multiple laser pulses and asking where is the average result, well, now things become a little bit different, because if you do this exact same experiment and these particles are diffusing through space such that they're no longer in exactly the same position as they were before, then what you'll get is a different speckle pattern. And now, if you sum, every time you hit the laser pulse, you're going to get a different speckle pattern. If you sum all of those, what you'll get is the incoherent sum of many individual source signatures. And those sources may locally be coherent, for example, from all the different molecules in the surface of a sphere, or they may be individual molecules that individually could generate a signal that is integrated over many individual molecules to generate the Hyper-Rayleigh scattering spectrum. So what's the difference between second harmonic generation and Hyper-Rayleigh scattering? Operationally, it's all based on coherence. And if you have an incoherent sum of many coupled oscillators, then that is the definition of Hyper-Rayleigh scattering. If you've got something that is coherent in the sense that every time you hit it, it is frozen relative to the experimental frame, then that is now a coherent summation. That would be called second harmonic generation. With that being said, this still represents a continuum. We can have experiments that produce signals that are cleanly polarized, or we can have experiments that produce signals that are completely depolarized. And there is a continuum from that entire spectrum that it actually leads very nicely into the description of Mueller matrices and Stokes vectors that is the next topic of conversation. But let's consider for now the case where things are incoherently summed, such that we're talking exclusively about Hyper-Rayleigh scattering, illustrated by this example, where you have many individual sources where their phase relationships relative to each other vary over time, and therefore result in incoherent addition at the detector. So if we make a Hyper-Rayleigh scattering measurement, what knobs can we turn? And the simplest is to change the incident polarization state and ask, if I tweak that, how does the intensity on each of my multiple detectors vary? And we really have three detectors that make the most sense in terms of measurement. One is a detector that detects the Y polarized component. Now, I should mention that we have a unique definition of our Cartesian coordinates compared to what we've done previously, in the sense that the Z and the Y define the plane of the sample, and X actually represents the direction of the beam propagation. Why this coordinate system? Because this wreaks havoc with everything we've done previously. Convenience, and I'm lazy, basically. So it turns out that it's a lot easier to calculate orientational averages with respect to Z component than X or Y. And so if we put that within the plane, within the scattering plane, the focal plane rather, then it becomes an easier analytical problem to solve. So that's really the primary motivation for putting Z within a reference frame that is distinct from what we've used previously. But the good news is, at the end of the day, once everything is done, the math doesn't care what particular coordinate system you choose. It cannot be dependent on a particular selection of coordinate systems. And so even though this description will be based on this particular selection of molecular coordinates, or laboratory coordinates rather, you should be aware that, of course, any arbitrary selection of molecular coordinates will yield exactly the same outcome. Okay, so with that being said, Z makes things easier, so we're going to stick with Z. Yeah. All right, what the heck is going on here? Okay, let's advance to the next slide. Thank you very much, PowerPoint. All right, so if we're doing second harmonic generation, Hyper-Rayleigh scattering that involves the detection at the doubled frequency, it turns out that in general we can write the intensity as a function of 5 parameters for each of the 2 detectors, which leads to a net sum of 10 independent observables. However, because of degeneracy associated with this orientational distribution, because we know that we have an isotropic system, the whole thing simplifies down considerably, such that it turns out there's really only 4 unique observables out of those 10 possible. Most of them are either 0 or degenerate. And so we end up with a smaller subset. And that's if we're coming in with, we're detecting on the Z polarization component, then we have 3 independent observables. And if we then rotate our axis of detection 90 degrees and allow ourselves to detect the X component, and that is co-parallel with the propagation direction of the optical beam, we get a 4th observable. So it's really 4 unique parameters that can be recovered from a Hyper-Rayleigh scattering measurement. And they're related back to these tensor elements and the laboratory frame by the relationships given by this equation.